for microcanonical. Remember, again, we are talking just micro. Because canonical, I write for the canonical rho will be function of the h, but I didn't mention that which kind of the function. So that will be comes in the next lectures. So, and this integration should be done over the range of that. Microcanonical is the ensemble or the system which is defined by its energy. Okay? You know, here I just repeated the E. So for the case which you have only the information or almost good information about the energy, you can say that this system is microcanonical. So this is a microcanonical. So if you can take this integral, because it's very hard, so you can find the omega, and this is a h. And with this omega, you can start to write the entropy, and from the entropy, you can get the energy, pressure, on everything. So this is the advanced method actually to find the omega. Before we never talk about that. Before we use it, the technique of counting, we say that the omega is the number of the accessible states which you can count by hand. So in the previous lecture, I told you that we explained that the omega is proportional always to v power n, because it looks like you have an n particle and you have a one box. So, and after that, we think about that it should be proportional to the volume of the n ball or 3 n-dimensional sphere. So very, it was a very bare idea. So very incomplete idea actually, and now we have the full idea. The full idea is that for microcanonical you needed to find, this is the omega. And this omega will be the function of the E and function of the N and probably function of the V. E and V. You know where the E, because E will comes from here, N will comes from the number, and the V, where the V will come? Yeah, from the DQ. D2Q will gives you the V. Actually, you have the V as a D2Q and something like that. Still it's hard. Why it's hard? Look at that. For example, this is the phase space I made for the system with Hamiltonian H, Q, and the P. This surface is correspond to the E minus delta over 2, and this is surface corresponds to E plus delta over 2. Like the simple harmonic oscillator, I told you to draw the phase portrait for that. It was elliptic. So you have for different energy, you have a different elliptic. But that's not very good shape, but anyway. Look at that. What you want is the volume between these two. You need the volume between them. Yes? Yes, because the integration is over between these two. So the elementary, the first strategy is that if you have the volume of one of them, for example, the volume of that, you can evaluate that for this, you evaluate that, and make a difference of the volumes. And it's very hard. It's very hard. You know, it looks like we have a 2r and r plus delta r, and I ask you find for me the area of that. What you will do? I say, okay, the area of one circle is pr squared, the smaller one. So the bigger one is pr plus delta r squared. So the one which I want is P. You see, this is looks like very old-fashioned, So it will be 2pr delta r plus p delta r squared, and finally you say that delta r is very, very smaller than r, so I can forget that 2pr delta r. Do you remember what that would be? This it will be dr delta r. The area between two infinitesimal surface can be obtained by taking the derivative of the area of one of them and multiply to the thickness. This is the thickness. I want to do the same. So if I find the volume of one of this surface, I make the derivative with respect to the E and multiply to the thickness. So You always are welcome to use the first equation I write it here, but I want to give you a better way. The better way to evaluate that is this. We just go through and find that this is a total Hamiltonian. Remember that this is a sigma of Qi and Pi and this. Just go and find that. That's very easy. This is the volume of one sphere from 0 to E, 0 to R. Like exactly remember the example which I solved it for you. So you can get that. I can call it this gamma, gamma E, N, and V, okay? But what you need is not that. You needed the Hamiltonian be bounded between E minus delta over 2 and this. So what's the thickness here? The thickness here will be the difference between the bond of the energy. This minus this, so will be delta. The thickness is delta. E plus delta over 2 minus E plus delta over 2. E by E cancel, so you remain just delta is the thickness. So the real omega, I go the upper real value, you see now. Delta so if you back to this is the equation. So you needed just to find the volume of one and just to make a derivative with respect to the other. But you remember, maybe you're one, I don't know, I hope all of you remember that. Several times I mentioned that in the statistical physics when n is big, so there is no difference between volume and area. Volume and area, I said. And that's true. Because when you take the derivative of this function, actually, even when you take the limit of n to tends to infinity, it doesn't sense very much change that if you just consider the function. But we needed to that because we need to have a very correct mathematical expressions. And look at that, delta is very small number. This is so, and what you are doing is that you are working always there with the logarithm of that, to find, because the starting is entropy. You need to first find entropy, after that you can develop the other equation. Making the logarithm of that, you will get some logarithm of this, okay, but you will get the logarithm of this. So always, when you take the derivative to find the pressure energy of something, that will disappear, because this is a constant. This is a constant. This thickness is just number, 1 electrovolt, I don't know, 2 electrovolt. Is the difference between two energy levels. Don't worry about that, but I was worried when I was a student. I was thinking always that why this delta appears. So I don't like it, this idea of that. But later I became very relaxed with that. Now I understood that it's better to, because do you know what I did when I was a student? I really find the volume of one, and I replaced this as a sphere, minus this as a sphere. And exactly like what I did it here for 3n dimensional, I did it that. So, and I find this, finally, one example, 2 examples, 3 examples, because I was not sure that this simple idea can be used in the higher dimension. Personally, I don't believe to higher dimensions. I don't believe that a system can have a huge number of the dimension and you can use the same mathematics. So that was my gut. I know that this works in 2 dimensions. I was not sure that it works in 6n dimension or something. So I used that only.